So good morning students. We'll continue further with our small signal analysis. So just a quick recap. Okay, what we have done previously. We have discussed about the expressions of transconductance parameter graphically and also mathematically. We just derived in our previous sessions, and the plots of GM versus VGS and ID, the effect of ID on transconductance parameter. Then the expressions of a JFET with respect to input impedance and output impedance, and then we looked at the small signal AC equivalent of a JFET. Okay, so it is being controlled by the input is actually a voltage controlled parameter, and at the output side, okay, in the linear region, the output impedance, which is RD, okay, it actually controls, whereas in the saturation part we have the constant current source, which is GM multiplied by VGS. Okay, then we discussed about how to draw the AC equivalent of a fixed bias configuration with JFETs. Okay, so that was the first configuration that we discussed, and I hope that students are clear with the DC analysis and the AC analysis concepts. Okay, how to perform the DC analysis and how to perform the AC analysis, because for the DC analysis, very quickly let me just remind you the things. Okay, for DC analysis, what do? We assume that C1 and C2, okay, usually these capacitors we consider them to be open circuits. Okay, and we also ignore, so that input and outputs will be ignored from the circuit. Okay, so that's for the DC analysis. Okay, so but this chapter is all about obtaining the small signal AC equivalent, okay, where the input is continuously changing with respect to time. So for AC analysis, what do? We consider C1, C2 and also the fixed biases. Okay, so wherever we have fixed bias, we consider all of them to be acting as short circuits. Okay, so that's how we usually start with our AC analysis. Okay, fine. So that was the AC equivalent circuit of a fixed bias configuration. The blue shaded region is the small signal AC equivalent of a JFET. Okay, I just denote it. So that's the AC equivalent of only a JFET. Okay, but to obtain the complete small signal AC equivalent of fixed bias configuration, you will have to replace the other components also with their equivalent ACs. Okay, which we have done, right? So here the battery is being replaced by a short circuit, the capacitors C1 and C2, and similarly the battery VDD. So all of them have been replaced by short circuits. Okay, so that was the small signal equivalent which we had obtained in the previous class. Okay, and then while AC analysis, the expressions, the common expressions which we obtain are the input impedance, the output impedance, and then the AC voltage gain. Okay, so these three are the common expressions for any of the configuration. Only thing is that the expressions will change. Okay, the parameters further. Okay, so today let us just quickly discuss about two more configurations which we had already studied with respect to DC analysis, right? So it is self-bias configuration. In self-bias configuration, we have two subparts. One is by bypassing the source resistance, and in the second case we will not try to bypass the RS. Okay, we will try to include its effect. Okay, so in this case, what will happen to the AC equivalent if we bypass RS? Okay, and what is RS? RS is the source resistance. See, in BJT, okay, RC coupled amplifier circuits, you must have come across the capacitance. Okay, suppose if it was a BJT, then the capacitance was CE. Okay, I hope students can recall this, where CE stands for emitter bypass capacitor. Emitter bypass capacitor. Okay, so this actually provides a low reactance path to the entire circuit, especially in the amplification purpose. So it provides a low reactance path. Okay, so that is with respect to a BJT. Now with respect to a JFET, it's not CE. Okay, the symbol is CS. Okay, so it is source bypass capacitor, right? Whereas the purpose is the same. It provides a low reactance path. Okay, it just avoids the drop across RS and provides a very low reactance path across the capacitance CS. Okay, which in turn helps in stabilizing the amplified output signal. Okay, so because of that we usually try to use the source bypass capacitor. Fine. Now what if we bypass RS? Okay, how do we bypass RS? Let us try to look at it. Okay, so what is being done? But for AC analysis, we know that if there are any capacitors, now CS is also a capacitor, right? So it has to be assumed to be a short circuit now. Okay, short circuit. Okay, please understand, we are bypassing RS. Okay, RS is being the source resistance is bypassed. Since it is bypassed, we'll have to consider CS, but for AC analysis the capacitor CS is being replaced by a short circuit. Okay, so let us just look at the circuit, how it appears. Okay, so C1 and C2 are being replaced by short circuit equivalents, no issues. RS, the source resistance, okay, instead of RS we have used the source capacitance CS, and now it is being short circuited. Okay, so that is the only difference here. Okay, rest everywhere all the other parameters are the same when compared to your fixed bias analysis. Everything is the same. One difference here is that we do not have VGG, right, as it was in the case of fixed bias configuration, but in the fixed bias also VGG was replaced by its equivalent short circuit, so we do not have this here. Okay, fine. So how does the redrawn network look like? Again, the blue shaded region indicates the AC equivalent of a JFET, and the other terms, the AC effects are being added. So RG is the gate resistance, input impedance, input voltage VI. Similarly, the capital RD is the drain resistance, Z0 output impedance, V0 is the output voltage. Okay, so as simple as that. So now it actually appears that the small signal equivalent is similar to that of a fixed bias configuration. Okay, so both the things are same. Now let us just look at the expressions for input impedance. Okay, Zi represents input impedance. Okay, so the expression is similar, right, because Zi is equal to the resistance offered at the input side considering V0 equal to 0. So Zi equal to Rg, right. So we have obtained this. Then Z0, okay, Z0 is again, right, where do we have Z0? Yes, so Z0 is the output impedance obtained considering the effect of input voltage to be 0, so that now it becomes RD parallel to small rd parallel to capital RD. Okay, so which is again the same. Now as per this condition, if small rd is greater than or equal to 10 rd, Z0 is almost equal to RD. Okay, see, one clarity which is to be given here is RD parallel to RD. See, these two are the resistances. Okay, usually small RD is the internal resistance of the JFET, and it is usually much larger when compared to RD, right? We know that if two resistors are in parallel, then the effective parallel resistance will be lesser than the least resistance value. Okay, basics of parallel resistance, right? Which means, see, if RD, okay, let me just say, see, usually RD will be much greater than RD, okay, capital RD, then Z0 is lesser than the least value, and here the least value is, so it is lesser than capital RD, okay, slightly lesser than capital RD, which we try to approximate it as almost equal to RD. Okay, practically it is slightly lesser than RD, but we'll just try to assume it. Okay, fine. Then what about the voltage gain? The voltage gain is again AV is equal to V0 upon Vi. So if you just go by the similar steps as we had done it for a fixed bias, we'll be getting the similar expressions. Okay, minus GM RD parallel to RD. Okay, please understand this Z0 is like this: RD, capital RD, small RD. Okay, that's the expression for two resistors which are in parallel, right? Okay, fine. Then what about the phase relationship? Just an information. The negative sign which is being given here. Okay, so this negative sign indicates that phase shift of 180 degrees appears or exists between input voltage and the output voltage. Okay, fine. Then coming to the second case, wherein we are not trying to bypass source resistance, unbypassed RS. Okay, so just consider when source resistance is unbypassed, then we are not considering the parallel capacitance at the source. Okay, we are not trying to short circuit because we are considering the resistance itself. Okay, so that is the small signal equivalent of unbypassed RS case. Okay, so what is being done here? Let me just erase them. See, as of now the circuit says self bias JFET configuration including the effects of RS. So since RS is included, it is being shown in the circuit with RD equal to infinite. Okay, with the JFET's internal resistance which is infinite. That means as of now this parallel resistance, okay, which should have appeared here, it is ignored as of now. Okay, for simplified analysis, ignored, okay, as of now, but finally it has to be considered. Okay, but for simplification purpose its effect is included. It is being assumed that its effect is infinite. Okay, so infinite, there is no current flowing. Okay, we just have only this path. So as per this analogy, how do we obtain the output expressions? Okay, there is a bit of mathematics here, so slightly involved, so you will have to focus. How do we express output impedance? Output impedance is expressed as Z0 equal to V0 upon I0 with Vi equal to 0. Then applying Kirchhoff's current law, what do we get? I0 plus ID, okay, is equal to GM into VGS. So let us just go back to the circuit. I0 plus ID, okay, please understand, I0 is the overall current, okay, and ID is the current flowing through the drain resistance. So it is being given here that the total current GM multiplied by VGS gives us the current source. This is equal to I0, okay, the current which is flowing here should be equal to I0 plus ID. Okay, so that's the basic expression with VGS. Okay, VGS is the input voltage which we are providing. This input voltage has to result, how do we define? Okay, this has to result in the overall expression of minus I naught plus ID into RS. Okay, so substituting, what do we get? I naught plus ID is equal to minus GM I naught plus ID into RS. Okay, so just bifurcating the expression and then simplifying and then solving, okay, we get this particular expression. Okay, it is just substitution based problem, you will have to practice it a while. Now one more important point here is I naught is equal to minus ID. Okay, so let us just check. See, the current directions are opposite, so I can express I naught equal to minus ID because the controlled current source, which is GM into VGS, is equal to 0 amperes. Okay, so if this effect is not there, then I can express that I naught equal to minus ID. Okay, so solving for V naught, what do I get further? Okay, V naught is this particular simple expression minus ID into RD. However, we have obtained I naught equal to minus ID. So based upon that, V naught equal to I naught into RD. So finally, the expression for output impedance is V naught by I naught. If you just go through this and then cancel out the common terms, you will be left with only RD. Okay, so as of now, you just forget about the mathematics. Okay, just concentrate on the terms being cancelled and the term which finally remains. The output, at the output impedance, we get the expression Z naught equal to RD. This is for unbypassed RS ignoring the effect of small rd. Okay, however, this cannot be ignored. Okay, what did we do? We initially considered RS, unbypassed RS, okay, and then try to obtain the expression for output impedance. But now this RD is in parallel, so it has to be considered. Okay, so what do we get when it is considered? Okay, so that's the circuit where we are considering the effect of RD. It has to be included now. Where? In this particular term. Okay, so again we have a little bit of mathematics. Okay, so where, yes, again the expression for output impedance is as given, applying Kirchhoff's current law. Okay, so just concentrate on the first expression, the one which is being highlighted. I naught, now it has to be expressed as GMVGS minus ID. Both these terms are same as that of the previous case, but the only additional current term is the current which is flowing through the resistance RD, small rd. Okay, so this is the extra term, right? Now how do we express VRD, voltage across, okay, the term? So that can be expressed as V naught plus VGS. Yeah, I'm sorry, see here actually this diagram should have been this one. Okay, so it has been wrongly pasted. Anyhow, what should be the voltage across RD? Okay, the voltage across RD is V naught plus VGS. What about I naught? Again, okay, the current I naught now has to be the one which is flowing across the current source path, across RD path, and across the capital RD, okay, which is the drain resistance path. Okay, so it is a sum of three components, right? I naught is sum of three current components. So the first one current source, second one, and the third one. Now again solving for I naught, okay, some substitution, solving for I naught, you will be getting this particular expression. However, VGS is minus ID plus I naught into RS. Okay, so that's the input expression. So when you substitute that, your final expression for I naught, output current, will be this one. Okay, so considering both the terms, one for I naught and one for minus ID, and then solving and then simplifying the things, and finally solving it for output impedance. See, our main objective is to obtain the output impedance Z0. For obtaining output impedance Z0, we need expressions for output voltage V0 and the output current I0. Okay, so output voltage I0 is straightforwardly expressed as minus ID into RD. However, obtaining expression for I0 is slightly difficult. Okay, this expression is obtained using all these mathematical steps. Okay, substitution steps, right? So here you can observe that these two terms are added, right? Okay, so this is for unbypassed RS, the complete expression for the output impedance. Okay, so this is what which is being given here. So that's the final output impedance expression for a self bias configuration. Similarly, voltage gain expression can be obtained. Okay, you already know what's the expression for VI. VI is always RG. And what about V0? Okay, so V0 is this particular expression. So when you take the ratio, you will be getting the complete expression. Again, if your small RD is much greater than 10 times RD plus RS, see, now you will have to consider the sum of both the resistances. Okay, because there is a source resistance also. In such case, the voltage gain expression gets simplified. Okay, see, these small signal analysis, they are slightly involved things, because you will have to substitute so many terms, but your in the final expressions, you should be very clear that what you want. Okay, the three terms that we want is input impedance, output impedance, and the voltage gain. Okay, all right. So next comes voltage divider configuration. Analysis of this voltage divider configuration is very simple, because we have already performed DC analysis of this particular configuration. The only difference is that we will have to short circuit the capacitances and then short circuit the fixed voltages, okay, which is being done here. So what's the expression for Zi? R1 parallel to R2. Okay, we know R1 parallel to R2. So input impedance is given as R1 parallel to R2. In other two configurations, it was Zi is equal to Rg, right? However, here we have two resistors, so it is R1 parallel to R2. Output impedance. Okay, how do you obtain output impedance? Set Vi equal to 0, which ensures that VGS and the current source parameter become 0, so that your output expression is again as simple as that, RD parallel to capital RD. Okay, so again, if this is greater, then the expression gets simplified. Okay, but just concentrate on the network now, the AC network or the AC small signal model. Of a voltage divider configuration. Okay, so that's the small signal of a JFET, and the other terms, when they are added, okay, we'll be getting such configuration. Okay, see, please understand, this circuit and the circuit which is mentioned in this particular slide, both are same. Sometimes you may feel that here both of them appear to be in series. No, they are in parallel, right? Because we are considering R1 parallel to R2 with respect to the node at the gate. Okay, so I can just consider it like this, right? This R1 resistor can be brought here, right? So it is again parallel. Okay, so this particular thing is being clearly shown here. R1 is parallel to R2. Fine. So finally the expression for voltage gain, again VGS equal to VI, output voltage is this particular expression. Okay, we are familiar with this expression now. Okay, there is no difficulty here. And again voltage gain is the ratio of output by input, so it is just a substitution problem. Okay, so there should not be any difficulty in this particular expression. The only complexity was for unbypassed source in the case of a self bias configuration. Okay, because we have a series of steps here. Okay, so except this configuration, everything else is pretty simple. Okay, fine. So I think we'll just stop here. Okay, today. If there is any doubt, you can ask me, students. In the next class, probably we'll try to discuss about one more JFET based configuration, which is again very important. Okay, it is called as source follower or common drain configuration. With respect to a BJT, its counterpart circuit is called as emitter follower. Okay, hope you students must be remembering it, emitter follower circuit, which you had studied in your basic electronics. Okay, see, this emitter follower circuit is again being used in many of the amplifiers. Okay, in BJT based amplifiers. So its JFET counterpart is called as source follower or common drain configuration. Okay, so it has some certain characteristics. So we'll try to discuss it in our next class. Okay, followed by the small signal AC equivalents of depletion type MOSFETs and also enhancement type MOSFETs. Okay, so we'll try to discuss are there any similarities, are there any differences between the small signal AC equivalents of depletion and enhancement type MOSFETs when compared to our traditional JFET AC equivalents. Okay, fine. So any doubts, students? Yes, so I think we'll stop here for this particular session.